Video we're going to be introduced to logarithmic functions. They are the inverse of the exponential functions that we just looked at in the previous video. I'll go through this box in a second, but I think I want to do just sort of a little bit more general introduction to this that isn't quite as formal as what I have in the box. So in the last section we had y equals 3 raised to the x, and when we made a table for that, it was negative 1, 0, 1 were the points that we tended to use. And then 3 to the negative 1 would be 1/3, 3 to the 0 would be 1, and 3 to the 1 would be 3. And what we got was a graph. This will be a very rough sketch that looked something like this. It had a horizontal asymptote right here. It always went through 0, 1, and the domain on that was all real numbers. The range was from 0 to infinity, but not including the 0. So if we found the inverse of this function like we did in a couple sections ago, it would be x equals 3 to the y. At the moment, we don't have a good way to solve for that y up there, and I'll show that in a second, but just to flip the x and y, we'll skip the solve step for a second. What that means is we would have this table but in reverse. So if I put in negative 1, 0, 1 for those y's, I'm going to get out the 1/3, 1, and 3 for the x's. And what that's going to look like is something like that, which, if you remember from graphing inverses, that is the inverse graph of this should look kind of like that, which is what a log is. So exponentials and logs are inverse functions. The exponential had a horizontal asymptote. The log graph is going to have a vertical asymptote. When I was saying that we don't have a great way to solve for that y, what we ended up doing is coming up with a new notation, and it's y equals log base b of x. And so what this reads as, this is starting to get into what's down here, log base b of x, it's asking, what do I raise this base to? What exponent do I raise the base to get this value? So it's very, very backwards from how we're used to thinking of it. This right here would be y is 1, log is base 3. What power do I raise 3 to get 3? And the answer is 1. So we're seeking exponents. Exponents are going to be our output in this case. Let me go through some of this down here now that I've done just sort of more of a general introduction. So we have this form, y equals log base b of x. I can write that as b raised to the x equals y, which is what we were just seeing up there. This one is going to be log form. This one's going to be exponential form. We'll do some work practicing switching back and forth between those a bunch because it ends up being pretty important. Just went through that. So logs and exponentials are inverse functions, so they're going to have inverse, the domains and ranges will be swapped, which is, we saw that just on this quick sketch of the graph. Exponentials, all real numbers, is the domain. So for log, all real numbers is the range. And the range on an exponential is 0 to infinity, not including the 0. And we're going to find the domain of the log is 0 to infinity, not including 0. Some definitions. The natural log is logarithm with base e. So base e, without going into the mysteries of e too much, e is a number like pi that is irrational. It never ends. It's 2.718 ... This ends up being a really useful number when we get to calculus. Again, I'm kind of not going to get too much into that at this moment, but just say that base e, we end up using natural logs far more often than we use what's going to be called common logs here in a second. And natural logs and base e are going to go together. So natural log, and it's written backwards, it's not an I, it's an ln. Let me write it a little bit bigger over here. Ln of x is the same thing as log base e of x. And so it's used so much that it gets its own notation of natural log. Ln x of y is going to be equivalent to e raised to the y equals x, so same thing in terms of switching back and forth between the forms. Here's just kind of a general little table of the different versions of logs we're going to see. So the general form, we're just using b to stand in for the base. And these exponential forms, they are not exponentials, they're still logs. The y is the output, the x is the input. But it's just writing in an exponential form, because we'll see sometimes that is useful. There's something called common log, and common log is base 10. So when you see a log written without a base, it has an invisible 10 down there. It's kind of like square root x. We don't put the 2 in the index because it's the most common one. It's just implied. And then natural log that we just looked at for a second there. Okay, so what do we do with this? For starters, we practice getting back and forth between log form and exponential form. And I have a little swoopy thing that I do that sort of helps me. It's the base. Remember, the answers are the exponents in logs. Logs find exponents. That's their job. So the base raised to the answer equals the argument. So 13 raised to the L would equal H. For this one, this is a common log. There's no base showing, so there's an implied 10 down there. So this would be 10 raised to the S equals R. Natural log, that's the one where there's that implied E down there. So this would be E raised to the B equals A. So these are just practicing getting from log form to exponential form, because sometimes one is more useful than the other depending on what you're doing. And now we're going backwards. So this is log base A. B is what equals C is what we're trying to get to. So for this, it helps to remember that the base stays the same. So this is going to be log base 4. It's the other two things. The answer becomes the argument, and the exponent is the answer to a log. So these two things are like they're switching sides, is sort of how I think of it. And the exponent has to be the equal side. So here we'd have, I'll write it log base 10 for a second of x equals y, and you could also absolutely write that log x equals y, which is a little more common to write it this way. Base e, so that means it's a natural log. So anytime we see the e, it goes with natural log of y equals x. So now we're going to solve logarithmic equations by converting to exponential form. So most of the log equations that we'll see in a few more sections are more complicated than these. But if we have something fairly simple like this, thinking of it in terms of exponential form will make way more sense to your brain rather than log form. So if I'm trying to solve for x in this, if I rewrite this 3 raised to the negative 4th equals x, now I have something that I can get my head around that I'm trying to solve for the x. Remember when we have a negative exponent, that's going to be 1 over 3/4 equals x. And so 3 raised to the 4th is 81. For this one, invisible 10 down there, so that is 10 cubed equals x. So this is 10 raised to the answer equals x, so x equals, oops, one more 0, 1,000. Okay, so x raised to the negative 5 would equal the argument. Put it up here. Let's rewrite that as a positive exponent, so 1 over x to the 5th, because remember we have a negative exponent in the numerator, we take it downstairs, and the denominator becomes positive, equals 1 over 243. And then here we're going to take the root, I'm going to just set these equal since the numerators are both 1s. I'll set the denominators equal and solve. And I have something to the 5th root, or to the 5th, so I want to use a 5th root to solve for that. And the 5th root undoes the 5 in the power, so that would be x. And then the 5th root of 243 is 3. Next up, we're going to have some more properties of logs. These, you don't see them a ton, but when you do, they're actually really easy to simplify once you are familiar with them. There's also these couple of things over here. Let me just take a second and go through a couple of these as to why they are. Log base b of b is 1, so let's make one up and make that make sense. This is what power do I raise 10 to get 10? And that's just going to be a very fancy way to write 1, because 10 to the first would make 10. So if the base and the argument are the same, it's literally saying what do I raise something to get itself, so that'd be 1. Log base 10 of 1, what power do I raise 10 to get 1? That would be 0, because remember, with any base raised to the 0, it's 1 as long as the base is not 0 or negative. And then natural log, those are working the same way. E matches the base, so ln e is 1. We'll run into that one a fair bit. Log of any of 1 is always going to be 0. For these inverse properties, I won't go through all of them, but let me show you just with one of them what they are doing over here, and then we'll go to the simplifies, which are actually super easy. So b raised to the log base b of x should be x. So here's how come. If I have 10 raised to log base 10 of 100, log base 10 of 100 asks, what power do I raise 10 to get 100? And that answer would be 2. And then we're raising 10 right back to that exact same exponent. And there we are back at 100. So b raised to log base b of x, the base, the log, and the exponential are kind of doing and then undoing each other. So you're just going to get the x. The same with the other 3 versions of this. It's just written, this one's log base b of b raised to, so you're raising first and then taking the log. So with that, then these down here become really straightforward. So for this, it's 10 log and then 73, so there's that invisible 10 down there in the base, which is just this. So that means it's just going to be 73. E raised to natural log, so that's this one, so it's just going to be the 1.59. Natural log of e to the 2.4, you can kind of guess it's going to be 2.4, but that's this one right here. And then we have a little bit of simplify, so with this, remember cube root is the same thing as a power of 1/3. So log 11 of 11 raised to the 1/3. So there's that base and the argument are the same. So that means it's just going to be 1/3. Log 1, remember log 1 is 0. So what power do I raise the base to? If this is base 10, what do I raise 10 to make it come out to 1? So this is just a big fancy 0 plus 7 would be 7. And natural log of 1, so again, if we have a log of 1, regardless if it's natural log or log base something else, that is a very fancy 0. This next question is just for you to get out your calculator and find your log and your natural log keys. And so if you bust out the calculator, you should see a log base 10, and then there might be a second function of that, or it may be its own button. It's probably its own button, and the second function would be e raised to something for this one. Anyhow, find those keys and toss them in the calculator. If you do this right, you should get 1.677 there. So that's asking what do I raise 10 to get 47.58. So 10 to the first would be 10, 10 to the second would be 100, so it makes sense that it'd be kind of in between there to get 47. And then this one, if you plug that in right, it should be 2.303. Again, the point of that is just to make you find where those buttons are on the calculator, as we'll need them later. Okay, now we're into the graphing of logs, which I kind of started off with. This will be a bit more in depth, and then those same transformations are back, I think, for the last time this quarter. So here, the first thing I would do if I'm going to graph a log is write it in exponential form. So 5 raised to the y, equals x. And it is much easier to pick y's and get out x's than it is to pick x's and then solve for y's in this case. So just letting y equal -1, we get 5 to the -1 would be 1/5. 5 to the 0, that would be 1 is what I would have to have on this side for that to come out. And then 5 to the 1st would be 5. So we're getting the exact same table we got for exponentials, except now the inputs are the old outputs and the old inputs are the domain and range swapped places. I'm not going to say that very well, but hopefully that made sense. Graphing this, we get, and again, I never like to start with a fraction. I start with the easy one. So right there, 1, 0, and then 5, 1. And then the 1/5 -1, that's the one that's going to be kind of close to the axis right there. And so we get a graph that looks something like that. We have a vertical asymptote this time instead of a horizontal asymptote. So this is the vertical is going to be the y-axis, or if you remember last time, the horizontal was the x-axis. Domain and range, like I said at the start of the video, have swapped. So the domain has to be greater than 0, and the range can be all real numbers. And the vertical asymptote, remember those take the form x equals, and so that's going to be x equals 0. Our horizontal asymptote last time was y equals 0. So you can see everything is just backwards, and that's because they are inverse functions to each other. So then graphing using transformations, it's the exact same things as we've done before. This right here is going to be a base 4, so let's just make a quick table, x, y, -1, 0, 1, and this will be 1/4, 1 and 4. I wish there was a way to make it not do that. So let's draw our parent function, and then we'll shift it down 3 units. So parent function would be 1, 4, 1/4. So kind of like that. And then -3 is going to shift everything down 3. So I'll just take each of the points and move them down 3. And we get that. For the graphing, this time you'll have to draw in the vertical asymptote. I did make a quick video showing the graphing, but it's very similar to the exponential. So you click on the vertical asymptote first and then 2 points on the graph. And same as I said last time, I'm going to show these kind of in terms of how you would graph them in an exam situation on paper and pencil. So for this next one, this is a -4 on the inside, so it's going to go right 4. And again with the same table, -1, 0, 1, 1/5, 1, and 5. And I'll do the 2 easy points first, and then that one that's kind of close to the asymptote. So you can see it's really close to this one. It's just instead of going over 4 and up 1, it's going to go over 5 and up 1 because we're base 5 instead of base 4. With this one, since we have a left-right shift, that means that the vertical asymptote is going to shift this time. So let me get that drawn in. It's going 4 to the right. And then I'll just move all these points over 4, which are just off the graph for that one. There and there. Let's see, so this one is going to go left 1 and down 3. And it's still base 5. So let me get that parent one drawn in. The vertical asymptote is going to shift with the left-right shift, so that's going to shift 1 to the left. And then all of our points are going to shift down 3 and left 1. So I'll just take this one and go down 1, 2, 3 and left 1, down 1, 2, 3 and left 1, and left 1. Again, don't start with a fraction because that's the hard one to count. Do the easy ones, and then this one's easy to see, or at least easier. And lastly, we have this one over here. So again, I'll do the parent function. Oops. This one is base 4. So it would look kind of like that. This one has a negative in front, so that's going to be our reflect across x. So let me draw that much. So that means this would reflect up here, and this would reflect down there. That one's kind of the hinge. And then we're going to take that and shift it down 3 units. So I'll just take each of these points and shift them down 3. And then that would be our transformed function. So same basic transformations we've been doing all quarter. A little bit harder function to draw, but same basic information. Last thing we have to look at is find the domain and vertical asymptotes of the function. So we've been seeing that the domain for these is that the x's have to be greater than 0. So that means whatever I plug in here into the argument has to stay greater than 0. So for domain, we'll just set the argument of the log to, not equals, no equals, just greater than 0, and solve and see where it comes out. So bringing the 6 over, we have 2x is greater than 6, and dividing both sides by 2, we would have x is greater than 3. So that means my domain is going to be from 3, parentheses because there's no equals, to infinity, and I have a vertical asymptote at x equals 3. For this one, 4 minus x is going to be greater than 0. Subtract the 4, minus x is greater than negative 4. And then we're going to multiply both sides by negative 1 to get rid of the sign. But we have to be a little careful when we do that, because when we multiply or divide an inequality by a negative, it reverses the direction of the inequality. So this is going to be, instead of greater than, x is less than 4. So our domain, which does make sense, if I put 3 into this function, it stays positive, right? 2, 1, negative 1, those would all be positive. But if I put in 5, it comes up negative. And that's because of that minus. So our domain here is going to be from negative infinity to 4. It's also, you can see that it has the negative on the x, so that's that reflection across the y-axis. And then vertical asymptote at x equals